Okay, your last part is being recorded as an MP3 because I can't really be bothered to set up the video. I'm looking at the slide after the Technetium 99 Now You Try question. So there's the two ways of measuring it. Two ways of measuring what? Damn it. Trying to think of the thing that I was trying to present with this, because it's kind of stage 1 physics moving into the stage 2. But anyway, if you go to the next slide where you see rocks, you'll notice that uranium has a long path all the way down to lead 206. And for example, if you go up to uranium-238 and you look at its passage, I think it's an alpha emission down to thorium, its half-life is 4.5 by 10 to the 9 years. Now that's a lot of years. And then you got a beta minus from thorium to palladium, and another beta minus from palladium back to uranium-234. So you've got 4.5 by 10 to the 9 years, and then you've got thorium and palladium, which are, you know, a matter of days and then a matter of hours. So it depends on the half-life itself, and you can see then if you go from uranium down to thorium down to radium down to radon and then to polonium, then you've got things like 2.5 by 10 to the 5 years, 8 by 10 to the 4 years, 1.6 by 10 to the 3 years. That's a long time. So this is why they can use the uranium cycle to radio date, not radiocarbon, but radio date rocks, because they have these known rocks from areas where, like, geologists agree, oh, it's this old, and depending on the amount of the various radioisotopes that they have in them, it can tell you sort of where along this path they are, therefore how old the rock is itself. This is also why the plate that I've got that radiates continues to be radioactive, because, you know, you've got lots and lots of years in terms of the half-life here. Now, let's go to the previous slide, so the two ways of measuring it. Oh, okay, so if you got anything that's older than 10,000 years, then you're going to be using that sort of radioisotope dating in the rocks. Now, it's not just the uranium series, there's about 3 or 4 other series that can be used from other isotopes that you can look at. You can use a Geiger counter to detect emissions in real time, and we use that unit, the becquerel, or the BQ, capital B, small q. That's so 1 becquerel is 1 disintegration, and you can have becquerel per hour, becquerel per minute, becquerel per second. You should be using becquerels in your graphs for your design prac. Now move past the slide on rocks and go to the slide on radiocarbon dating. Carbon has got 3 stable isotopes, 12, 13 and 14. Carbon-14 is the radioactive isotope which is generated from nitrogen up in the atmosphere by exposure to cosmic rays. And now, obviously the sun has flares and has varying amounts of emissions of solar winds, but in general, over the entire Earth, the amount of carbon-14 produced of any particular day or month is about the same. And the rate at which you take in carbon, because when you eat things with carbon on it, the carbon becomes part of your body. Some of that carbon will be carbon-14, only a very small amount, but some of it will. And as you continue to eat and your body replenishes its atoms, and you know, you excrete other atoms, or your skin falls off and stuff, you know, because it does fall off. It's like, what do they call it, sloughs off. Your skin's constantly replenishing too. You're just a walking giant dust farm, and that's ignoring all the sort of little mites and stuff that live in your eyebrow thing where the hair grows, skin follicles and all that sort of stuff. Yeah, let's get back on topic. You're going to acquire this carbon at a constant rate. But when you die, you stop eating, unsurprisingly. And therefore that carbon does no longer get put into your body and continue to replenish, and so it starts to drop off. And what we can do then with that in mind is we're able to look at the amount of carbon-14 that's left and give you an approximate date for the biological stuff. Now, we move to the next slide. It says application positron emission tomography. So the body, that's the next slide, the human body atom recycling plant. The body is one giant chemical factory. You are what you eat, and you excrete what you don't need. Mostly you're just empty space. Now, when you've got an isotope like carbon-13 or carbon-14, your body doesn't tell the difference between them. It doesn't go, oh, well, carbon-14 is a radioactive isotope, I don't want to absorb it. It just absorbs it like it would any other carbon atom. So, moving on to the next slide. There are examples of where certain elements will actually exist in higher concentrations in the body, and a great example is the thyroid gland. Now, the thyroid gland keeps high amounts of iodine, but after Chernobyl and accidents like that, it releases a lot of iodine fallout, and that's like a radioactive form of iodine, but the body would still take it in through food and exposure and dust and whatnot, and the iodine will gather in your thyroid gland and it will sit there radiating, and that's really bad because, you know, the glands, thyroid glands and stuff, very sensitive to radiation, and so it's easy to get cancer. And so that's why they give iodine pills to people like they did in Japan after the Fukushima incident, because you basically just flood your body with a crap load of non-radioactive iodine, which will eventually over time displace all the radioactive iodine, which you will then basically piss out of your body. You can also use radioactive isotopes for medical purposes. So you create it, you inject it into a person, and you want it to go to the right part of the body, because, I mean, it's not, you know, unless you want to light the whole damn body up, then you want it to go to the right area. And it is effectively like turning on a light bulb, but it's in the non-visible spectrum. And in this case, in general, what's used is gamma rays. And so the gamma rays will shine out of the body because they've got a phenomenal penetration ability, so it's not difficult for a gamma ray to leave the inside of the human body. And with the gamma ray detector, you can then draw a 3D picture of what's going on in the human body. Alright, given the fact that this podcast must be limited to 10 minutes, I'll have to stop and restart a new recording. And I will do that right now. Okay, now I'm looking at the slide, beta positive for a more positive world. So, before Jason gets too carried away, you're just going to have to accept the fact that a positron is a positive electron. It's the antimatter particle of an electron. It is just the way it is. Asking why it does things or why it exists in that manner, well, these are questions for particle physicists, not for me. I don't have the intellectual capacity to answer that to a level which would satisfy you. And I think in a lot of these things anyway, if you really wanted to be fully satisfied of what it was properly, you would need a degree or a doctorate in theoretical physics, because to fully understand the positron and the manner of radioactive decay using the weak nuclear force and the changing of the internals of, you know, your subatomic particles with quarks and all that sort of stuff, well, yeah, you really need to go get yourself a university physics education, and I only have a year of that. So, you know, don't be surprised when I can't tell you what a neutrino really is. Like, I know what an orange is, and I know what an apple is, and, you know, I know what an electron is, I guess. But then really, when you think about it and you think, well, what the hell is an electron really? I mean, how do you answer that? It's a negative positron. So, you know, it's like that question, what is energy? Well, it's this thing, and you get tested on it, then you can go and get a career in something, and everyone's happy. So, when matter meets antimatter, it annihilates to create free energy. Yeah, free energy for you, and that's where they come from. The antimatter bomb comes from. You know, they just detonate and create a whole bunch of antimatter somewhere, which combines with all the matter, and then the world lights up. When a positron collides with an electron, i.e. the electron, which is the matter particle, combines with the positron, which is an antimatter particle. And for this matter, you need to know why positron decay occurs. Yeah, why would something want to give away from the nucleus of an atom a positron as opposed to a beta minus electron emission? That's something you need to know. But you get these two identical, when the electron and the positron come together, high-energy gamma-ray photons. And they travel in opposite directions. Due to the law of conservation of momentum. Because the energy comes out, and because the particles are apparently at this point when they are come together not moving. I don't really see how this can be the case, but it is. It creates these two gamma rays, and they flow out in equal and opposite directions, and also the gamma rays will have the same frequency. And if you go to the next slide, which is the PET scan, positron emission tomography, the way this works is you get a person and you give them their nuclear dye, and then they lie on the bed, and then they're surrounded by a ring of detectors. Now if you go to the next slide, you'll see, that could be an area where the nuclear dye is gone to, and then every time a positron is emitted and collides with an electron in that location, it creates two equal and opposite gamma rays, which are then detected by the photomultiplier ring. And of course, over thousands, if not millions of readings of gamma rays, you can eventually, after triangulating their originating location, draw a 3D picture of what it is that they're radiating in. Now apparently a full PET scan will take up to 1 hour and form over 1 million coincidence lines. Really, I don't think that's the case, because when I was at the Royal Adelaide Hospital, it depends on who's on the table, but if it's a small kid, 20 minutes, half an hour at most. If it's like a tremendously large individual, it takes more time for the gamma rays and to get out. And eventually, you get a person as a certain size can't get a PET scan because they don't fit in the hole of the machine. And I don't think they've actually made sort of bariatric PET scanners that take morbidly obese people. That hasn't been something that they've made yet. So I think that tremendously overweight aspect will make a PET scan unavailable to you. Now if you go to the next slide, it says old technology and PET scan results. You'll see the old technology is the sort of x-rays, soft tissue x-ray, and you're not seeing much in terms of they are a nuclear dye scan there, or an x-ray dye, I think, but they're fairly fuzzy images and don't show you much. The PET scan is of a much higher resolution and much easier for doctors that do diagnosis. Now, medical isotope slide. Oxygen-15 is commonly used. Its half-life is 2 minutes, and it's injected to track circulation system. You can also breathe it in, and that'll light the lungs up. Fluorine-18 is the common one, which is what they attach to what they call FDG. You attach it to a glucose molecule. Now that's great because muscles use glucose to move and generate energy. And of course, cancer, being constantly on the grow, constantly uses glucose. So if you get someone and you make them lie down, and they have to lie down for half an hour, if not longer, and not move at all, and then you inject the glucose containing with the fluorine 18 stuck to it, you inject them with that, all the glucose will go to the areas which are most active, and if the person's lying down and not moving, then all their muscles aren't active, but the cancer remains active, and so it then starts mopping up all this radioactive glucose, and hence the gamma rays start shining out of where the cancer is. So it's a great way to find cancer. Now, in general, a PET scanner will need to be next to a cyclotron so that you can have these isotopes produced next to the scanner itself. If you go to the next slide, you can see the cyclotrons which make oxygen-15 and fluorine-18. They're very expensive, require a lot of maintenance. I mean, you can see why like Darwin doesn't have one just for the hell of it. But then, sometimes there's stuff like technetium, for example, that gets delivered and the nuclear substance will last for a couple of days. So, that gets made at Lucas Heights. Like, it just depends on the isotope you want and for what medical process you use. Anyway, down to the slide that says PET scan. And its clever mathematical algorithms can take this information and reconstruct the original radioactivity map. In this example, we see an 18-fluorodeoxyglucose, i.e. the FDG, radioactivity distribution inside the human brain. Hotspots correspond to areas of increased metabolic activity. They can also use this to find, I think, blood clots in the brain, like strokes and stuff. The next slide are pretty pictures of the scanner that they have at the Royal Adelaide Hospital, which I visited. And if you go on the YouTube playlist, you'll see a half-hour long video that I recorded where the radiographer took me for a tour through the facility, and we looked at all of this stuff. And that's a really old machine. Royal Adelaide Hospital is going to get rebuilt and get a brand new machine, and they're all very excited. The new machines can do PET scans a lot faster. You've got 2 rings on that machine, because one ring's for gamma rays and one ring is actually a CT scanner, so it does X-rays, and then it sort of combines the image from the gamma rays and the X-rays to create an even higher resolution image, which then allows you to get an idea of what's going on. I think the most tragic thing about this whole situation is, as interesting as nuclear medicine is, it's often injected into people who are getting scans because they're really, really sick. And you know, I saw a documentary on, was a short news story on a girl who was going under these scans. She's like 3 years old, only just learning to talk, and she's, you know, she's got some hideous cancer. That's the thing, I mean, kids and cancer, you know, what did that kid do to deserve that cancer? And then they get put on this machine, and oh, it's so scary. Anyway, you can save lives if you're a radiologist. You should consider this as a career. Check my YouTube playlist for additional things which are interesting, but don't necessarily bear any relevance to your test. Alright, thank you, and thus ends the lesson.